Hi guys, today I'm going to show you how to use the formula to calculate the area of a parallelogram. We already talked in a previous video about how you can find the area using other strategies like decomposing the parallelogram and rearranging it, taking the triangle off, moving it over to make it into a rectangle. But today we're going to actually introduce the formula itself. And I've done a little bit of the prep work for you ahead of time using this page from your math book. So it says to identify a base and a corresponding height and record their lengths in the table. So I've identified a base in each figure. Remember that a base can be any side of a parallelogram, but it's often helpful to look at if it's the one on the bottom. However, if it's a figure that doesn't have like a bottom that is clearly horizontal, and instead if it's an oblique line, it might be easier to pick a base that actually has like straight vertical or horizontal line. So that's why I've chosen this base. And then I chose a height for each of the parallelograms as well. You remember that the height has to meet the base at a 90-degree angle. So I drew in a little 90-degree angle here. Here's my height. I picked this spot. Here's my height. I could have done the height here. I could have drawn it here. There are many different heights, places to indicate the height, I should say. Here I have a base with the corresponding height over on the outside of the parallelogram. And same thing here. The height is on the outside of the parallelogram, which is okay. We can have a height on the outside. Okay, so then record their lengths in the table, find the area of the parallelogram, and record it in the last column. So I counted the base for each of the parallelograms and the height. So 4, 1, 2, 3, 4, 6 is the height. I recorded that here. That was simple enough to calculate. It's a rectangle, so 6 times 4 is 24. That's the area. Here on this one, the base was 5, the height was 3. And if you imagine taking the triangle over and filling it in here, then we would have a 5 by 3 rectangle and the area would be 15. This one's a little bit harder to envision how you would rearrange it. We talked about rearranging this kind of parallelogram in class using this sort of method here where you cut it apart and just sort of slide all the pieces over so they make like a stack on top of each other. I'm not going to go through doing that, actually drawing that out on this piece, but it would turn into a rectangle that has a parallelogram of 6 square units. And then finally this base and height, same thing. If I cut off this triangle here and move it over so that it fills in the space where I drew the height, I would have a rectangle that's 4 by 2 and the area would be 8. So I wrote that down. So then it's asking for an expression down here for the area of any parallelogram. If B is the base and H is the height. So if you look at the pattern, what is happening here? Every time you have a base and a height and an area, what is the relationship between the base and the height and the area? And hopefully you can see that the pattern in the table is that in every time, the base times the height equals the area. Even for the parallelograms that were like really slanty, like this one, even for the parallelograms that are actually a rectangle, which is a special kind of parallelogram, base times height equals the area. So our expression for the area of any parallelogram would be base times height equals the area. So I'm going to rewrite it down here. The formula for the area of a parallelogram is base times height. And I have used the dot, which means to multiply. When we have letters that we are talking about in mathematical equations, if I said base times height equals area, it's a little confusing. Like, is that x? Does that mean another variable? Or is it the symbol for multiplication? We're going to be starting to transition in 6th grade to the dot as a multiplication symbol instead of the x for that very reason. So it doesn't mix us up. Hey, I hope this was helpful.